Hi, students. So today we're going to do section 7.7, which is complex fractions. Complex fractions are really important for you guys to understand. You're going to come across fractions later in college algebra. You see a ton of fractions in calculus. Fractions come up all the time, and it's best to just dive in head first and get really comfortable with them because this is something that's not going to go away. And once you're comfortable with these, it's going to make your algebra skills just so much better. Okay, so really take the time to understand what's going on and work with these complex fractions. Before we get started with examples, I'm going to go over just a little bit of kind of definition stuff. So let me share my screen with you. All right, there we go. So complex fractions. A complex fraction is a fraction with one or more fractions inside the numerator or the denominator. So a complex fraction is where you've got fractions inside of fractions. We don't like this. It's very uncomfortable and awkward. So we like to do what we call simplifying complex fractions. So a complex fraction has been simplified. And first of all, the numerator and the denominator don't have any fractions inside of them, right? You just have your one main fraction bar. And also the fraction itself is simplified, meaning that you don't have any common factors between the numerator and the denominator, okay? So for example, the complex fraction where the numerator is x plus 1/2 and the denominator is x plus 1, that's going to simplify to 2x plus 1 over 2x plus 2. Okay, I'll show you how that simplifies, but that's just an example of the first fraction there is a complex fraction because that 1/2 is inside the numerator, and that's kind of awkward. But the second fraction does not have any fractions inside of it. Just so you know, those two fractions that you see on the screen right now are equivalent. Okay, if you plugged in a value for x in each of those fractions, the same value for x is going to make both of those fractions the same value. Okay, so those are equivalent fractions. I'll show you how we get from one to the other. And just a little side note, that second fraction, 2x plus 1 over 2x plus 2, is simplified. If something inside you wants to cancel out those 2's or that 2x, think again. The numerator is completely factored, right? The factor in the numerator is 2x plus 1. That's one complete factor. The denominator does contain two factors, 2 and an x plus 1, which we've distributed to become 2x plus 2. But the numerator and the denominator do not share any common factors anymore. So if something inside you wants to cancel stuff out in that second fraction that you see, really think again and check yourself on simplifying fractions. Okay. So that's simplifying fractions. Let's do some examples. But before we do some examples, let me explain to you the techniques we're going to use to simplify our complex fractions. We have two methods. Technically, at any time, you could use either of these two methods, but I'm going to show you when you should use each because certain situations lend themselves to one method over the other. So the first method, you have to first have your numerator into a single fraction or a single term and your denominator into a single fraction or a single term. And then you look at that main fraction bar and you say that essentially means division. So you just rewrite it as a division of fractions problem. So the numerator divided by the denominator, and you turn it into a division problem. Okay, so that's the first technique. that works best when your numerator and your denominator are already inside of single fractions, so a fraction divided by a fraction. The second method, which I think sometimes we use a little bit more as we move on because we just get comfortable with it, is going to be what I call the LCD method. So here we look at all of our interior fractions, find their LCD, and then we multiply our fraction, our main fraction bar, by LCD over LCD, and that cancels out the denominator of the interior fractions. So this method too is very similar to what we do when we're solving equations with rational expressions, where we multiply both sides of the equation by LCD over LCD, okay? So those are our two techniques. Let's go into an example. So I'm going to share my whiteboard with you. And let's just work on that example that you guys saw there, which is the x plus 1/2 over x plus 1. Okay. So we'll do the first method first, and then I'll do the second method. And you'll see in both cases, it's going to simplify to 2x plus 1 over 2x plus 2. Okay. So the first method tells us that we want to view our main fraction bar, this guy, as division. Okay. So essentially what we want to do in our first method is we want to say we've got x plus 1/2 is being divided by x plus 1. Okay. But we need to actually combine this into one piece so that we can do the fraction division. So our issue here is that we've got two terms on the left. We've got these two terms here, and we've got two terms on the right. So we need to turn these each into one single term. And that term can be a single fraction. So on the right-hand side, what we're actually just going to do is call this x plus 1. We're going to call that an x plus 1 over 1. So now we've got a single fraction that is our denominator. Let me clean that up for you. All right, so our denominator is x plus 1 over 1. But on the left, that x plus 1/2 also needs to become a single fraction. And we already know, how do we add two things that are fractions? Well, we find the LCD, right? We find the LCD. So we're trying to add x plus 1/2. Our LCD here is 2. So we need to change this fraction, which is just an x, into a fraction with a denominator of 2. So we're just going to multiply this x by a 2 over 2. Right? And that stuff in green is essentially just multiplying by a version of 1, right? We multiplied by 2 over 2. So now we can combine the x plus 1/2. And that's going to become a 2x plus 1. So this whole thing here is going to be 2x plus 1 over 2. All right. And the remaining is going to be x plus 1 over 1. Okay. If we wanted to do that while maintaining our fraction bar symbolism instead of our division symbolism, it would look like this. So our numerator would turn into that, and our denominator would turn into x plus 1 over 1. Okay. So that's essentially what we just did. We just rewrote our numerator and denominator as single fractions. The denominator just became a fraction over 1, and the numerator, we had to add those two terms by finding a common denominator with that 1/2, just in the numerator. But this whole thing, then we look at that as a division problem. So remember how our division problems work. We just flip the thing we're dividing by and make it a multiplication problem. So we've got 2x plus 1 over 2 times 1 over x plus 1, right? Remember, we're going to multiply straight across. And since we have more than one term in the numerator and the denominator, you really want to remember that those fraction bars are grouping symbols. So this 2 is going to get distributed to the x and to the 1. So in the numerator, we've got 2x plus 1 times 1. So that remains a 2x plus 1. In the denominator, we've got the 2 times the x and the 2 times the 1. So that becomes 2x plus 2. And now we just do a quick check. Do we have any common factors here? The numerator can't be factored any further. These share no common factors, so 2x plus 1 is the only factor of the numerator. The denominator can be factored. It can be factored to a 2 times an x plus 1. But neither of those factors are factors of the numerator. So this guy is completely factored, and now we no longer have fractions inside of fractions. Notice that the only thing we did was multiply by this version of 1, perform the division that is this division bar, and division really is multiplication. Okay, so we didn't change anything. This new fraction that we have is equivalent to our original fraction, but our original fraction was complex. This new fraction is completely simplified. Okay, so that's using method 1, where we turn the division bar into a division problem. In order for that to work, we have to make the numerator a single fraction, the denominator a single fraction, so that we can make it into a division problem. Okay. Let's do that same example, but use method 2, where we multiply by the LCD of all of our interior fractions in the form of multiplication by, so we multiply by LCD over LCD. Right, so our problem is still x plus 1/2 over x plus 1, right? So here we're going to use the LCD method, and we actually want to look at all of our interior fractions. Okay, so every single term on the inside is going to be an interior fraction. All right. So when we look at all our interior fractions, we really only have one interior fraction that has a denominator that isn't 1, and that's this 1/2. So our LCD, when we look at all the fractions in the bottom and in the top, is just 2. So we're going to multiply by our version of 1, which is LCD over LCD. And when we do that, we're actually multiplying over the main fraction bar. So we're going to multiply by 2 over 2. And this is going to get distributed into the numerator here and into the numerator of the denominators. Okay. What I mean by that is, if you have fractions inside of fractions and you're multiplying them by a whole number, anytime you multiply a fraction by a whole number, you multiply it into the numerator of that fraction. Okay. So we multiply straight across, and we're going to have to distribute that 2. So we're going to get a 2x plus, now 1/2 times 2 is going to be a 2 over 2 or a 1. And in the denominator, we're going to get the 2x plus 2. Right. So just like last time, we just multiplied by this version of 1 here, and we've gotten rid of the interior fractions, and we've come out with a simplified fraction that is no longer a complex fraction. right? If it's weird for you how the 2, so 2 times x gave us the 2x. 2 times 1/2 gave us the 1. If you're uncomfortable with multiplying like that, you can take an extra step and write out the distributed process. So let me show you how that would look. We have x plus 1/2 over x plus 1. And this is all getting multiplied by. Now, if you want to, you can write it as we're multiplying by 2 over 1 over 2 over 1. Okay. And when we distribute that stuff, we get that x times 2 over 1. So we get an x times 2. Let me put it in your color. So we get the x times 2 over 1 plus the 1/2 times 2 over 1. And all that is over another x times 2 over 1 plus 1 times 2 over 1. So depending on how you like to see your fractions, and if you're having trouble figuring out if things are supposed to get multiplied into the numerator or multiplied into the denominator, remember that when you have a whole number multiplied by a fraction, it's going into the numerator, okay? Because a whole number is really a number over 1. So you can visualize it like this, multiplying by 2 over 2, or you can visualize it as multiplying by 2 over 1. You can take an extra step to rewrite the distributed step if you need to, or if you're comfortable saying 1/2 times 2 is 1, you can go straight to there. Okay. So that's example 1. And again, you end up with the same thing. This becomes a 2x, this becomes a 1, this becomes a 2x, and this becomes a 2. Okay. So those are the 2 methods for simplifying your complex fractions. Let me do 2 different problems to show you when each method is ideal. All right. So in this next example, method 1 is going to be ideal, and I will show you why. So in this example, we've got a complex fraction. Take note where your main fraction bar is. This is our main fraction bar. So the numerator is 5 over x plus 2, and the denominator is 10 over x minus 2. Those are the 2 fractions that we're dealing with. In this case, method 1 is actually easier. Method 1 is easier because, as you can see, we've got a single fraction on the top and a single fraction on the bottom. So we're already set up to treat that main fraction bar as division. Another reason that method 1 is easier, the LCD of our interior fractions would be x plus 1 over x minus 2. That's a messy LCD, and that'd be a lot to work with. So here we want to use method 1, and it's going to come out to look like this. So we just treat that main fraction bar right here as a division. And since we already have a single fraction in the numerator, a single fraction in the denominator, we've just got a fraction divided by a fraction. That very easily turns into multiplication, right? Because that's what fraction division is. It's multiplication by the reciprocal. And again, remember that those fraction bars are grouping symbols. So those 2 terms need to have parentheses before you multiply straight across, so that when you do multiply straight across, you remember to distribute. So the numerator becomes 5x minus 10, because that's 5 times negative 2. and the denominator becomes 10x plus 20. And that is no longer a complex fraction, but take note that we do have common factors in the numerator and the denominator. If we wanted to, we could have realized we've got a factor of 5 in the numerator and a factor of 10 in the denominator, and we could have actually simplified those to begin with. Those both have a factor of 5 in them, so we could have removed that factor of 5 to begin with. Or we can remove that factor of 5 later. But what we're going to end up with is a x minus 2 over, you can say x plus 2 times 2, or you can say a 2x plus 4. So we can say this is x minus 2 over x plus 2 times 2 if we want to. Either one of these is correct. This is just has a factored numerator. This has a distributed numerator. Both of these are correct. They are simplified in that they no longer have complex fractions, and they're also simplified in that the numerator and the denominator don't share common factors. Okay. So this was a case where method 1 was the easiest method to use because we already had a fraction divided by a fraction. Let's take a look at another method or another problem where the LCD method is actually going to be the faster way to go. All right, so in this case, our numerator is x over y squared plus 1 over y. We've got 2 fractions in our numerator. Our denominator is y over x squared plus 1 over x. We've got 2 fractions in our denominator. If we wanted to use method 1 here, we would have to add the fractions in the numerator, add the fractions in the denominator, and then use division. That takes a lot of work. That's why here the LCD method, method 2, is the better. All right, so here, it would take a lot of work to get this into a fraction divided by a fraction situation. And all our interior fractions have monomial denominators. So finding an LCD isn't going to be that bad. So for this example, using method 2, where we multiply by LCD over LCD, is the best way to go. And just in case you can't quite tell, that's an x squared right there. There we go. Okay, so when we look at all our denominators, we've got a y squared, a y, an x squared, and an x. So that means that our LCD is going to be y squared, x squared. Right? That's a multiple of all our denominators there. So we're going to multiply over the main fraction bar, y squared x squared over y squared x squared. And here's where, when you have all these fractions, if you need to, just remember that this is the same thing as y squared x squared over 1 divided by y squared x squared over 1. If you need that 1 as a placeholder to remind yourself that this y squared x squared goes into the numerator here, and same thing in the bottom, you can do that. Okay. So now we also need to remember that grouping symbol, right? That fraction bar is a grouping. So we're going to distribute the y squared x squared to each of the terms in the numerators and to each of the terms in the denominator. Okay, so let's take a look at what that's going to look like. And let's move this out of the way. Okay. When we distribute it to our first term, we've got an x over y squared. And that guy is being multiplied by our y squared x squared. Then that's added to our 1 over y, which we're distributing, multiply y squared x squared. All of that is over our denominator, which is y over x squared. And we're going to distribute in our multiplication by y squared x squared. And for that very last fraction, that 1 over x is also going to get multiplied by our y squared x squared. Right. So each term essentially gets multiplied by the LCD, right? And in doing so, a lot of stuff is going to cancel out. So in our first fraction, this y squared will cancel out with this y squared. In our second fraction, the y will cancel out with one of those y's. In the denominator, the x squared will cancel out with this x squared. And I'm sorry, that doesn't look like an x, does it? That's our x. And this x will cancel out with one of these x's. So let's regroup to see everything we have. Our first term, what we're left with is an x times x squared. So our first term is x to the third. Our second term, what we're left with is just an x squared. So our second term is going to be an x squared. Then in the denominator, our first term, we're left with a y times a y squared. So that's going to be a y to the third. And our second term, we're left with a y squared times an x. And I did make a mistake there. This term up here, right, we just canceled that one factor of y. So we still have a factor of y. So this is y times x squared up here. All right, so we've eliminated the complexity from this fraction. All we had to do was multiply by LCD over LCD. Just be very careful to distribute that to every term in the numerator, every term in the denominator, and keep in mind that LCD is kind of like an over 1. It goes into the numerator. If you're multiplying by a whole number, it goes into the numerator, okay? So we've got this guy in blue, x to the third plus yx squared over y to the third plus y squared x. It's a little tricky to see what's going on, but let's put this on let's factor this on a new whiteboard, and we'll see if we've got anything that we can cancel out. All right, so we've got x to the third plus yx squared over y to the third plus y squared x. In the numerator, if we remember, when you factor binomials, unless you're in the special case where we've got a difference of squares or a sum or difference of cubes, really all you can do with a binomial is factor out a GCF. So both of these terms have two factors of x. So we're going to factor off an x squared in the numerator. Okay. Now in the denominator, we also have a binomial. They both have factors of a y squared. So we're going to factor off a factor of y in the denominator. Now take a look at what factors we have. We've got two factors of an x and a single factor of x plus y. In the denominator, we've got two factors of y and a single factor of y plus x. X plus y and y plus x are the same thing. They're common factors. We can cancel them out. This whole thing simplifies to x squared over y squared, right? And if you just want to keep in mind where we started, our original problem was this. That's what we started with. It all simplifies to x squared over y squared. We used the LCD method because we had so many different fraction pieces, but all of their denominators were monomials, so it was easy to find the LCD. And once we just distributed and then simplified all our interior fractions, we just had to do that very last factoring step, and it simplified quite nicely to x squared over y squared. All right. All right, so that's an example of using where you want to use method 2, the LCD method. The next video will be working with negative exponents, but definitely take your time to review this video and make sure you understand each step that we did, and maybe go over just a few homework problems to kind of practice these exercises. All right, good luck with everything.